Evening everyone. Today we are going to see about design of FIR filters using Windows. Okay, this is the most important topic in DTSP in the third unit for EC students and fourth unit for EEE students. Compulsory, you may receive this type of question in any university question papers. Okay, first we'll see the procedure to design a FIR filter using Windows. The first step is to from the given specification in the problem, we have to draw the desired frequency response. Okay, next we have to find the desired impulse response of a FIR filter, that is SDFN. Third step is we have to find the impulse response of a FIR filter h of n equal to SD of n into WH of n for n varies from 0 to n minus 1, 0 otherwise. And fourth step is to from the obtained h of n value in the previous step, we have to find the transfer function h of z. That is h of z equal to summation n varies from 0 to n minus 1 h of n into z power minus n. From this transfer function, we have to draw the linear phase structure. With this, the design of FIR will be over. Next, sometimes in the problem, they may ask to find the FIR coefficients. So from the transfer function, we can able to write the FIR filter coefficients. Sometimes they may ask the frequency response of a filter. The frequency response of a FIR filter can be found using the formula h e power j omega equal to a power 0 plus summation equal to 1 minus a n cos n. So a of is nothing but h of n minus 1 by 2 and a of is to h of n minus 1 minus. From this information, we'll see example problem to solve filter using. Now see one example. So I'll read the problem now. Design an ideal band filter having upper and lower frequencies of 0.4 radian per second and 0.2 radian per second. Assume the length of filter is 7 and also the filter coefficients. Okay, this is a problem given. First of all, we have to write data given, okay, given data. What is the type of filter? So type of filter is we have to assign band pass filter. So write it as BPF. And type of window. So we already known we have four types of window, that is Hanning window, Hamming window, Blackman window and rectangular window. So here we are asked to perform this problem using Hamming window. So type of window is Hamming. So length of the filter is something but n, so that is 7. Upper cutoff frequency and lower cutoff frequencies are given. So omega c1 is lower cutoff frequency, that is 0.2 radian per second, and upper cutoff frequency is 0.4 radian per second. Here HD of e power j omega value was not given in the problem directly, so it comes under indirect method. So these are the given data in the problem. Okay, now we'll go for solution. So what is the first step? From the given specification, draw the desired frequency response of FIR filter. Okay, so first step is draw the desired frequency response of band pass filter. Okay, so here this is minus 0.4, this is minus 0.2, this is omega c2 minus omega c2, this is minus omega c1. So plus omega c1 plus omega c2. So this is plus 0.2 plus 0.4. So it varies from minus pi to plus pi. So band pass filter means this band of frequency is allowed by the filter. So this is the desired frequency response of band pass filter. Next, we have to write desired frequency response, that is SD of e power j omega. For any type of filter, SD of e power j omega is e power minus j alpha omega for let us write, and 0 otherwise. Before writing this, we should know the basic concepts of filters. Okay, so for low pass filter means this is a frequency variation. It varies from minus omega c to plus omega c, and for high pass filter, modulus of omega varies from omega c to pi. Band pass filter means modulus of omega varies from omega c1 to omega c2, and band stop filter means modulus of omega is less than or equal to omega c1, and modulus of omega varies from omega c2 to pi. These are the different types of frequency variations for different types of filters. Here we are using, okay, so for band pass filter, this is a frequency variation. Modulus of omega varies from omega c1 to omega c2. So write that frequency variation, omega c1 less than or equal to modulus of omega less than or equal to omega c2, where alpha is nothing but n minus 1 divided by 2. These are the basic formulas. Next, we have to substitute n value in this equation so that we can find alpha value, and we have to substitute this alpha and omega c1 and omega c2 in this equation so that we can find the desired frequency response of a FIR filter. So what is alpha? N minus 1 by 2. So what is the n value given in the problem? That is 7. So 7 minus 1 by 2. So we can write alpha equal to, what is 7 minus 1? 6. 6 by 2 is 3. So alpha equal to 3. Yeah, now substitute alpha equal to 3 and omega c1 equal to 0.2 and omega c2 equal to 0.4. Yeah, take it as equation 1. So we have to substitute these values in equation 1. So SD of e power j omega is equal to, we can write e power minus j alpha value is 3 omega for omega c1 0.2 less than or equal to modulus of omega less than or equal to 0.4, 0 otherwise. Yeah, take it as equation 2. Next, second step, for band pass filter, SD of n equal to, okay, you just see here. So it comes under indirect method because SD of e power j omega value was not given directly in the. For band pass filter, desired impulse response SDFN equal to, this is the formula in indirect method. Sine of omega c2 of n minus alpha minus sine of omega c1 of n minus alpha by pi of n minus alpha if n is not equal to alpha, omega c2 minus omega c1 by pi if n equal to alpha. Okay, now we have to write this formula. So SDFN equal to sine omega c2 f sine omega c1 of n minus alpha whole divided by pi of n minus alpha if n is not equal to alpha, and omega c2 minus omega c1 by pi if n equal to alpha. Now we know the values of alpha, omega c1 and omega c2. Take it as equation 3. Substitute these values in equation 3. So that is SD of n equal to sine of What is omega c2? That is 0.4. N minus alpha value is 3 minus sine of omega c1 value is 0.2 n minus 3 whole divided by pi of n minus 3 if n is not equal to 3. Omega c2 value is 0.4 minus 0.2 by pi if n equal to 3. Okay, next we have to third step is we have to find the impulse response h of n of FIR filter. So third step is take it as equation 4. Third step, h of n equal to SD of n into WH of n for n varies from 0 to n minus 1, 0 otherwise. This is the third step, finding the impulse response of digital FIR filter. So we already know that n value is 7. So substitute n equal to 7 in that equation. So we will get h of n equal to SD of n into WH of n for n varies from 0 to 6. Take it as equation 5. So we have to substitute HDFN and WHFN in equation 6. We already derived HDFN value, that is sine of 0.4 into n minus 3 minus sine of 0.2 into n minus 3 by pi of n minus 3 if by n is not equal to 3. 0.4 minus 0.2 by pi if n equal to 3. That is HDFN value. This WHFN is nothing but the basic window equation. So here we are asked us to find the type of window is given as Hamming window. So we have to write a basic Hamming window equation now. So for Hamming window, the window equation is WH of n equal to, we already know this equation, 0.54 minus 0.46 cos of 2 pi n by n minus 1. Okay, now substitute capital N equal to 7 in this equation. So WH of n equal to 0.54 minus 0.46 cos of 2 pi n divided by 6. Take it as equation number 6. Okay, now substitute equation 4 and 6 in equation 5. Okay, so what is equation 5? H of n equal to SD of n into WH of n for n varies from 0 to 6. Okay, so here small n is varying from 0 to 6. So n, it varies from 0 to 6. 0, 1, 2, 3, 4, 5, 6. Next we have to find HD of n value if n equal to 0 to 6. Next we have to find the window value, that is WH of n, and H of n is equal to SD of n into WH of n. Okay, now what is if n equal to 3, what is SD of n? 0.4 minus 0.2 by pi. Okay, now take your calculator, substitute 0.4 minus 0.2 whole divided by pi. So we are getting 0.0636. Okay, so that is the value of n equal to 3, 636. Next we have to type this equation in our calculator. Instead of n, I am going to take substitute the value capital X. Okay, before that ensure that your calculator must be in radian mode. Okay, so the keeping your calculator in radian mode is mandatory in solving the problems in digital signal processing. Okay, now this is the basic HDFN equation. Yeah, So before substituting this equation in formula, you please write like this: sin open bracket, what is omega c2? 0.4 open bracket. Instead of n, I am going to substitute the variable x minus 3. Okay, already one open bracket is there, so close bracket. So sin of 0.2 of x minus 3, already one open bracket is there, close bracket, divided by pi of x minus 3. Yeah, so we have to type this the equation present in this box in our calculator. Okay, before that, ensure our calculator must be in ready in mode. Okay, after we type this equation, press the calci option in our calculator. Below the shift button we have calci option. If you press calci option, we'll get x question mark. So what value you have to find? For x equal to 0, we have to find the value. So x equal to 0, if I substitute, I will get 0.038. 0.38. X equal to 1 means I will get 0.052. For x equal to 2, I will get 0.060. X equal to 3 already we found, that is 0.0636. For 4, I will get 0.060. For 5, 0.052. And for 6, we will get 0.038. Next, we have to type the basic window equation. What is window equation? 0.54 minus 0.46 cos 2 pi. Instead of n, we have to substitute the value x divided by 6. So x equal to 0, so we will get 0.08, and x equal to 1, we will get 0.31, and x equal to 2, so we will get 0.77, and x equal to 3, we will get 1. So for x equal to 4, we will get 0.77, 0.31, 0.08. Now we have to get the impulse response HFN, we have to multiply SDFN with WHFN. So multiply these two values, we will get 0.038 into 0.08, 0.038 into 0.08. So we will get 3.04 into 10 power minus 3, that is 0.003. Next, 0.052 into 0.31, so we will get 0.016. Next, 0.06 into 0.77, so we will get 0.046, so we will get 0.0636 here, so we will get 0.046, 0.016, 0.003. So this is the value of the h of n. Next, we have, what is the next step? We have to find the transfer function h of z. So fourth step is transfer function h of z equal to summation n equal to 0 to n minus 1 h of n into z power minus n. So we already known small capital N equal to 7, so small n varies from 0 to 6, h of n into z power minus n will come. Okay. So now expand this equation. So h of z equal to we will get h of 0 into z power 0 plus h of 1 into z power minus 1 up to we will get h of 6 into z power minus 6. So therefore h of z equal to, so what is h of 0? h of 0 is 0.003, 0.003 into z power 0 is 1. And what is h of 1? 0.016 is h of 1. So 0.016 z power minus 1. So next h of 2 into z power minus 2 is the h of 2 value is 0.046. So we'll write 0.046 into z power minus 2. So next one is h of 3 into z power minus 3. What is h of 3? 0.0636. 0.0636 into z power minus 3 plus next h of 4. H of 4 is 0.046 into z power minus 4 and h of 5 into z power minus 5, that is 0.016 into z power minus 5 plus h of 6 is 0.03 into z power minus 6. So now we can take 0.003 outside from this equation, so that we will get 1 plus z power minus 6. Next 0.016 if we take outside, we will get z power minus 1 plus z power minus 5. Next we can take 0.046 outside, so we will get z power minus 2 plus z power minus 4, z power minus 2 plus z power minus 4 plus 0.0636 into z power minus 3 will come. Next we can find the FIR filter coefficients. FIR filter coefficients. So what is coefficient of z power minus 3 is nothing but h of 3. So h of 3 equal to 0.0636. Coefficient of z power 0 and z power 6 is 0.03. So h of 0 equal to h of 6 equal to, we'll get 0.003. And coefficient of z power minus 1 and coefficient of z power minus 5 is 0.016. So we can write as h of 1 equal to h of 5 equal to 0.016. And coefficient of z power minus 2 and coefficient of z power minus 4 is 0.046. So we can write h of 2 equal to h of 4 equal to 0.046. Okay, so this is fifth step. And sixth step is we have to draw the linear phase structure. So this is the final step in this problem. So we have to draw the linear phase structure. Yeah, so already we found the transfer function of digital FIR filter. So here the maximum power of ZNS is 6. So we have to draw 3 ZNS in the first line, and the maximum, if n equal to 7, we have to draw 3 ZNS in the first line and another 3 ZNS in the second line. I will tell one shortcut. If n equal to 7, divide this 7 with 2. So 7 by 2 is quotient is 3 and remainder is 1. So let us take this quotient. Okay, so 3 z inverse 3, the quotient value is 3, so 3 z inverse in the first line and another 3 z inverse in the second line. For example, if n equal to 11, n equal to 11 means what is the quotient when it is divided by 2? Yes, the quotient is 5. So for if n equal to 11, we have to draw 5 z inverse in the first line and another 5 z inverse in the second line. Okay, so in this problem n value is given as 7. So we have to draw 3 z inverse in the first line and another 3 z inverse in the second line. Okay, next, so here input is x of z. When it is multiplied with for example, here input is 1. When 1 is multiplied with z power minus 1, we will get z power minus 1. When z power minus 1 is multiplied with z power minus 2, z power minus 1, we will get here we will get z power minus 2. When z power minus 2 is multiplied with z power minus 1, we will get z power minus 3. So here we will get z power minus 4. Here we will get z power minus 5. So finally z power minus 5 is multiplied with z power minus 1 means we will get z power minus 6. Okay, so we have to add 1 with z power minus 6. So this 1 is added with z power minus 6. So the output of this adder is 1 plus z power minus 6, and this term is multiplied with 0.003. Okay. Next, z power minus 1 is added with z power minus 5. So this z power minus 1 is given to the input of the adder, and z power minus 5 is also given to the input of another adder. So output of this adder is z power minus 1 plus z power minus 5. It is multiplied with 0.016. Similarly, here z power minus 2 is added with z power minus 4, and this addition is multiplied with 0.046. Now we are adding z power minus 2 and z power minus 4. So here we are getting 0.046, and z power minus 3 is multiplied with 0.0636. Now we want to add everything, then only we will get h of z. Okay. So finally we will get y of z. So in this way we have to solve the design of digital band pass FIR filter using Hamilton tool. Okay, if you like this video, please put a like, comment and share. Don't forget to subscribe our channel. Thank you.